Okay. Thanks for coming back from the coffee. Now we start with the second part of our session. I will start with a short talk about the basics and some new developments on cluster expansion. Then Axel Hübner will talk about the cross-validation methods and how this is useful for selecting clusters and selecting structures to calculate. And then Maria Troppens will talk about thermodynamics in using cluster expansion. Okay, so I will start with a basic explanation what is the usefulness of cluster expansion in material science with an example of a phase diagram for a binary alloy. Then I will perform a cluster expansion by hand, and then how this is generalized with data analytics methods. So in material science, compound is expressed with a chemical formula. Here we have an example of this where A and B indicate different chemical species, and X the quantity of those species. So, but the chemical formula is not everything, since we have many more things in the material. For instance, the crystal structure. Given a compound, it could form different structures, as shown here for diamond, rock salt, zinc blende. Also, once we know the crystal structure, we may wonder which sites the different species in the crystal would occupy. We could have either some ordered structures or some disordered structures. Besides the crystal structure, we may also wonder about other physical properties, as depending on the configuration of the material, whether the material is a metal or an insulator. And if we are more ambitious, we could ask what happens when we heat up the material. Much of this information is contained in the phase diagram, in the temperature concentration phase diagram, that is shown here, where on the left part of the x-axis we have pure A, and on the right side we have pure B material. So the different regions in this diagram indicate different stable phases that could be present. And if we focus at a given temperature, we will have first in this region pure A. And this region would be an example of a pure order phase in the middle range of the concentration. That could be this, for instance, the checkerboard. Or also on the right extreme of the x-axis, we have pure B. And these gaps here show phase separation regions where we could have a bit of phase alpha and a bit of phase beta, as shown here. So, and as you can see, there is a temperature axis that would tell us what are the concentration ranges for different phases at different temperatures. This is an example of a phase diagram obtained with the cluster expansion method for a copper-lithium binary alloy. As you can see, one can obtain quite a complex description of the material. But in order to be able to construct this phase diagram, we need first to know what is the energy of formation of any arbitrary configuration of the crystal. Also, we would like to know what are the most stable ones at zero temperature to know where the phase diagram starts. Also, we may wonder about the different properties for different concentrations and different temperatures. So, as you can imagine, this is difficult to obtain, since if we consider a crystal lattice, that with a parent lattice as indicated here, you see this crystal is a repetition of this parent lattice. And then we consider a supercell of this crystal composed of 4x4 lattice sides. The number of possible configurations for atoms of the type A and B in the crystal is quite large. If you consider that you have two possibilities for each size, this is 2 to the n without counting symmetries. So this amounts to more than 65,000 configurations just for 16 sides. Therefore, we can, of course, not make initial calculations for all of them. Then, therefore, we use the cluster expansion method. So in this, now I will go to this cluster expansion by hand. So what we would do, we take a cluster, a supercell, the one that I showed before, and then we calculate the ab initio energy. So this is the calculated energy, and we basically define a cluster interaction that we call J0 with the number that we just calculated. Then we replace one atom A by an atom B, and then we calculate the ab initio energy again. We have this number, so the difference will give us a new interaction that we call J1. Now we put two atoms, so we have the pristine crystal plus twice the interaction J1. Then we have an additional term that we call C2, and that we can obtain this term because we know the ab initio energy that we calculated for this structure. We know this number, so the difference will give us this parameter. We can continue adding parameters by performing different configurations. And also, we could even consider many body interactions. For instance, here we have the pristine structure, 3 times the J1, the 3 different pair interactions, and then we have an additional term. Once we have this number, we can build an arbitrary structure, and by counting how many interactions we have of this kind, of every kind, then we can make a prediction. So this would be our predicted energy using this cluster expansion that we built. However, this is not done in this way. In reality, we are more systematic. So what we do is we have to define certain elements. One of those are the clusters that are just structural patterns that are indicated with crystal size as this. Here is an example. For instance, this cluster is composed by size 1 and 2. And we also have to consider the multiplicities, which are the repetitions of this cluster by applying all the symmetry operations of the crystal. In this case, for this 2-point cluster, we will have 16 of those repetitions. Another element that we use is the configuration vector, as was presented before. But I make a small difference. Instead of using the representation -1, 1, here I use a representation 0, 1 that is easier to interpret and is also a valid basis for the cluster expansion. So here this indicates that, the side 1 is occupied with atom A, side 2 is occupied with atom B, then 0, 0, 0, 1, 1, 0, and so on. So this basically represents our configuration. Then we define the cluster correlations. The cluster correlations in this representation that I'm using tells us how many times this pattern, for instance, corresponding to cluster alpha, is present in the structure S. This can be calculated in this way, but the basic thing that we have to take is that this would be a sort of the frequency in which this cluster appears in a given structure. Using these elements, then we can write the predicted energy as the product of the multiplicities times the correlations times the interaction coefficients. That this is basically a nicer way to write what we wrote before. So these numbers that you see here will be the product of the multiplicity by the cluster correlations. Now, what we do also for the structures, we do not build the structures just as one side and two and so on, but we just have a training set that can be arbitrary structures. And with this training set, we build a vector of energies. Then we have a pool of clusters that can be many. And then we build this matrix, the correlation matrix, that every column is a cluster and every row is a sample of the training set. Then we write as before, but we must find what are the cluster interactions. So how do we do that? We minimize, in principle, the mean square error. This is the easiest way to do it. And there is an analytical solution for this that is written in terms of the correlation matrix. However, this matrix cannot be inverted when the number of clusters is larger than the number of structures. Also, another problem is it is highly sensitive to noise and leads to overfitting. So the solution is to add regularization terms, as here the L2 norm. That also has an analytical solution that this time this matrix can be inverted if you have more clusters than structures. So you can play a lot more with different models. However, also finding the best fit doesn't guarantee to have a good predictability power. So what we do is to construct a validation set, and then we measure the error or the distance between the predictions and this validation set. This is called the cross-validation score that will be the subject of Axel. But as you can see here, we should look at all possible cluster sets that minimize this quantity. This can be also estimated with the Lib1R cross-validation as written here. And this cross-validation score, that is the error of the predictions, can detect what is called overfitting. If we have a small number of clusters, the root mean square error will be high because the fitting is not good. We have a small number of parameters, and also the cross-validation score. If we increase the number of clusters, the root mean square error will go down and down and down because our model has more and more parameters, so we can fit better and better. However, at a certain point, the cross-validation will start to increase again, and this is the overfitting. And there is a point when we reach a minimum, this you will see in the tutorial, that gives us what is the optimal set of clusters. So we usually use this technique when using L2 penalization to select the clusters that are good for our model. But as I told you before, one have to build many cluster sets, and this is what is called an NP-hard problem, because the number of sets also explodes in a combinatorial way. And also to reduce the number of the pool of clusters, we should use physical intuition, and we would like to have a more systematic way to do it. So the way to do it is where some machine learning techniques enter in the cluster expansion approach. We replace the L2 norm by the L1 norm. So this is so then we can use lasso. So instead of using the Euclidean distance, we use the Manhattan distance. This basically is the length of the interactions, let's say. And this is very convenient because we can also reformulate this problem as a constraint problem, that we are minimizing the root mean square error constrained to this Manhattan norm, and this gives automatically sparsity in the model. So some of the interactions will automatically go to 0, and this doesn't happen when we use the Euclidean norm that leads to dense models. So with the compressed sensing, what we have is at the same time the optimal ECIs and the optimal set of clusters. This has also efficient noise filtering. The drawback in front of the L2 norm is that it must be solved numerically. So these are the people that are working in this part of the code. Okay, I wanted to acknowledge the developers. This is all these things are implemented in this code. This is being developed in the group of Claudia Draxel, and these are the developers. Thank you.